Stars are giant balls of burning gas. They are composed primarily of hydrogen and helium, the two lightest elements in the universe. Through the process of nuclear fusion, stars convert hydrogen into helium, releasing an immense amount of energy in the form of light and heat. They shine brightly, lighting up the universe. This light can travel across vast distances, allowing us to see stars that are millions or even billions of light years away. The brightness of a star is a testament to the incredible energy it produces. But stars don't live forever. Over millions or even billions of years, a star will exhaust its nuclear fuel. As it runs out of hydrogen, it begins to burn helium and other heavier elements, but this process cannot go on indefinitely. When a star runs out of fuel, it can explode in a spectacular event called a supernova. This explosion occurs when the core of the star collapses under its own gravity, leading to a massive release of energy. A supernova is a powerful and luminous explosion that marks the end of a star's life. The energy released during a supernova can outshine an entire galaxy for a short period of time. Imagine a massive explosion, millions of times brighter than our sun. That's a supernova. The light from a supernova can be so intense that it can be seen across vast distances in the universe, even with the naked eye. They are among the most energetic events in the cosmos. The energy released in a supernova is so immense that it can trigger the formation of new stars and planets from the surrounding gas and dust. These extraordinary events are not only visually stunning but also play a crucial role in shaping the universe as we know it. The elements created in the heart of a star and dispersed by a supernova are essential for the formation of planets and life itself. Without supernovae, the universe would be a very different place. Stars are born from clouds of gas and dust. These vast regions, known as stellar nurseries or nebulae, are the birthplaces of stars. Within these clouds, particles of gas and dust begin to clump together under the force of gravity. Over time, these clumps grow larger and denser, eventually forming a protostar. Gravity pulls the gas and dust together, causing it to heat up. As the material collapses, the temperature and pressure at the core of the protostar increase. This process continues for millions of years, with the core becoming hotter and denser. Eventually, the core of the star becomes so hot that nuclear fusion begins. This marks the birth of a new star. During nuclear fusion, hydrogen atoms combine to form helium, releasing a tremendous amount of energy in the process. This process releases energy and makes the star shine. The energy produced in the core radiates outward, balancing the gravitational forces pulling the star inward. This balance allows the star to remain stable for most of its life. Stars spend most of their lives fusing hydrogen into helium in their cores. This phase is known as the main sequence, and it can last for billions of years. During this time, the star remains relatively stable, with a constant output of energy. However, stars eventually run out of hydrogen fuel. When this happens, the star can no longer sustain nuclear fusion in its core. The balance between gravity and pressure is disrupted, leading to significant changes in the star's structure. When this happens, the core of the star contracts and heats up even more. The outer layers of the star expand and cool, transforming the star into a red giant. This phase is much shorter than the main sequence, lasting only a few million years. This can cause the star to expand into a red giant. The outer layers of the star are pushed outward and the star becomes much larger and more luminous. However, the core continues to contract and heat up, eventually leading to the next stage of stellar evolution. Eventually, the outer layers of the star are blown off into space, leaving behind a white dwarf. This remnant is incredibly dense and hot, but it no longer undergoes nuclear fusion. Over billions of years, the white dwarf will cool and fade, marking the end of the star's life cycle. There are two main types of supernovae, Type 1 and Type 2. Type Ia supernovae occur in binary star systems. A white dwarf star pulls material from its companion star. If the white dwarf accumulates enough mass, it can trigger a runaway nuclear fusion reaction, resulting in a spectacular explosion. Type 2 supernovae occur when massive stars, much larger than our Sun, run out of fuel in their cores. The core collapses under its own gravity, triggering a shock wave that rips through the star, blasting it apart. Supernovae are incredibly bright. In fact, they can outshine entire galaxies for weeks or even months. This intense brightness makes them visible across vast cosmic distances, providing astronomers with valuable tools to study the universe. Imagine a single star shining brighter than billions of stars combined. This incredible luminosity allows astronomers to detect supernovae in distant galaxies, providing insights into the early universe and the evolution of stars over cosmic time. The light from these distant explosions carries information about the composition and expansion of the cosmos. Section 5. Stellar Alchemy, Forging Elements in the Crucible of Supernovae. Supernovae are not only destructive events but also cosmic creators. The intense heat and pressure within a supernova explosion forge heavy elements like gold, silver, and uranium. These elements are scattered into space by the supernova explosion. These elements then become part of new stars, planets, and even life. The calcium in our bones, the iron in our blood, and the silicon in our computers were all created in the hearts of dying stars. Section 6. Cosmic Architects, Supernovae, and the Formation of New Stars. Supernovae play a crucial role in triggering the birth of new stars. When a supernova explodes, it sends out shock waves into the surrounding gas and dust. These shock waves can compress the gas and dust, causing it to collapse and form new stars. In a way, supernovae are like cosmic gardeners, scattering the seeds of new stars and planets across the cosmos. Their explosive deaths pave the way for new generations of stars to be born. Section 7. Echoes of Creation, Supernova Remnants. After a supernova explosion, what's left behind? The remnants of the exploded star can linger for thousands of years, forming beautiful and intricate structures called supernova remnants. These remnants are like cosmic fingerprints, revealing clues about the original star and the nature of its explosion. These remnants continue to interact with their surroundings, shaping the interstellar medium and influencing the evolution of galaxies. Studying these remnants provides valuable information about the processes that drive stellar evolution and the enrichment of the cosmos. Section 8. Windows to the Past, Supernovae as Cosmic Yardsticks. Because supernovae are so bright and consistent in their brightness, astronomers use them as standard candles to measure cosmic distances. By observing how bright a supernova appears from Earth, astronomers can calculate how far away it is. This helps us understand the vast distances between galaxies and the overall structure of the universe. Supernova act like cosmic mile markers, allowing us to chart the universe's expansion and evolution. Section 9. Unraveling the Mysteries of the Universe, the Importance of Studying Supernovae. Supernovae are incredibly important for understanding the universe. These stellar explosions are not just spectacular light shows, they are key events that shape the cosmos. When a star reaches the end of its life and explodes, it releases an immense amount of energy and material into space. They are cosmic laboratories that allow us to study extreme physics and the creation of elements. The intense heat and pressure during a supernova explosion forge new elements, some of which are essential for life as we know it. For instance, elements like carbon, oxygen, and iron are formed in these fiery crucibles. By studying supernovae, we can learn about the lives and deaths of stars, gaining insights into their life cycles. This knowledge helps us understand how stars evolve over millions or even billions of years. Observing these events also allows astronomers to test theories of stellar evolution and refine their models. The history of our galaxy and how it has been shaped by these powerful explosions. Supernovae have played a crucial role in distributing elements throughout the galaxy, enriching the interstellar medium, and contributing to the formation of new stars and planetary systems, and the expansion of the universe. The light from distant supernovae provides valuable data on the rate of expansion, helping scientists understand the dynamics of the cosmos. This information is vital for studying dark energy, the mysterious force driving the accelerated expansion of the universe. These cosmic explosions hold clues to the fundamental laws of physics, offering a natural laboratory for testing theories of gravity, nuclear physics, and particle interactions. The remnants of supernovae, such as neutron stars and black holes, are also of great interest to researchers, and the origins of the elements that make up our world. The debris from supernovae seeds the cosmos with the building blocks of planets and life. Without these explosions, the universe would lack the diversity of elements necessary for complex chemistry and biology. As we continue to observe and study supernovae, we gain a deeper understanding of the cosmos and our place within it. Each new discovery brings us closer to answering fundamental questions about the nature of the universe, the origins of matter, and the processes that have shaped our existence. The study of supernovae is not just about looking outward into space. It's also about looking inward, to understand the very fabric of reality and our connection to the stars.